for a collar mic or a static mic? Right? Yeah. ठीक है इसको फिर इसको बंद कर ठीक कम जावेद ठीक Okay, good afternoon everyone. I request all of you to be seated please and be ready for the presentation. Yeah, yeah. Okay. So I'm Indrajit Roy, and I hope that there are some some participants from colleges of different colleges from DU. I believe there are some, okay, and as well as from the department. So I welcome all of you. Maybe for some of you, first time to the seminar hall, okay, so or to the department. So welcome everyone. We are very happy to have Professor Javid Zaib, who is the chair of Chemistry Department at State University of New York at Buffalo. Okay? And to introduce Professor Zaib, I'll call Professor Ramakant to the honor.
This lecture is arranged under the series of Centenary Year series. And all of you know there are several programs are going on in university during Centenary Year. And Department of Chemistry has also in Centenary Year. So we have this series of lecture and some other program to celebrate Centenary Year for the department. And so I will read citation for Professor Javed Rajazev. And he currently serves as the chair of Department of Chemistry at the State University of New York, SUNY Buffalo. He received his PhD in Polymer Science and Engineering from the University of Massachusetts in 2004. And after finishing his postdoctoral training at the University of Minnesota, he joined the Department of Chemistry at SUNY Buffalo in 2006. His research program embraces all the steps of a successful material design, from building tailored polymers, structures, and architecture to analyze their supramolecular organization, to testing their macro-scale properties. Over the year, his group has developed extensive synthetic expertise that allow one to push the limits of what is achievable in terms of creating multi-component macromolecule with well-defined dimensions, shapes, and compositions. These macromolecules are being used as building block to create nanostructured material to benefit a variety of applications, such as conversion of commodity plastic waste into valuable materials, filtration, water purification, energy storage, as well as polymer recycling. For his research, he is richly recognized with a number of awards, which include National Science Foundation Career Award in 2009, Young Investigator Award in 2012, Fellow of Polymer Chemistry, Division of ACS, 2012, and Exceptional Scholar Sustained Achievement Award in 2021. So I welcome Professor Javed Rajazev to come on the dais. So we can give him. Please continue.
All right, hello everyone. Thank you for welcoming me. Thanks for this great honor. I'm really happy to be here and to be able to share my research with you. So I am from the University at Buffalo. I want to tell you first a few things about our department. Okay, if there are any undergraduate students in the audience, this is particularly might be interesting for you. So this is just an artwork that one of our talented faculty members created that combines all of the research going on in the department. So Buffalo is located in New York State. Right? This is New York State. Buffalo is right here. New York City is on the other side of the state. We are right on the border between US and Canada. Buffalo is designated as a flagship campuses across the state, and University at Buffalo is the largest and most comprehensive campus of SUNY, and therefore it's been designated as a flagship school. So a little bit more about our department. We're located actually not in the city of Buffalo, but on the outskirts in a suburb called Amherst. This is a chemistry building, natural sciences complex. It was built in the late 90s, where our home is. It's occupied. It's called Natural Sciences Complex, but it's basically Department of Chemistry. Going back in history, University at Buffalo was established in 1846, but it was established as a private medical college. And for a long time, it had a medical school and other professional schools that are geared towards health sciences. And because chemistry education is integral to health sciences, chemistry has always been part of the University at Buffalo. So first PhD awarded by the University at Buffalo was in 1926. And first PhD from Buffalo was a PhD in chemistry, right? So you're celebrating your 100th year anniversary, and we're getting ready to celebrate 100th year anniversary of our graduate program in a few years. All right, so our current department has 29 research faculty members, 4 teaching faculty members, over 130 graduate students. Almost all of them are PhD students. We have very small master's program. Most of our graduate students are PhD students. Our faculty do impactful research that gathers citations and funding from federal agencies to allow us to conduct exciting research in various areas of chemistry. And by any quantifiable metric, citations, publications, grants, and so on, UB is ranked in the top 25 of public universities in the US. This is our Twitter handle. You can follow us on Twitter until Twitter collapses. So our department is undergone some reconstruction recently. So we've, most of the chemistry departments are divided into disciplines: organic, inorganic, physical, analytical, and so forth. And a few years back, we kind of rethought that process and thought that with all the interest in interdisciplinary research, we should be bringing disciplines together and not dividing them, right? And so what we did is we got rid of the disciplines and instead created 5 what we call atoms. ATOM stands for academic teams of multidisciplinary scientists. And the atoms are shown here: biological and medicinal chemistry atom, energy and sustainability, materials and nano, spectroscopy and measurements and synthesis, both organic and inorganic. And so every faculty member is part of 2 atoms. And so they get to talk to folks that do similar kind of research, but maybe in different subdisciplines of chemistry. All this is to say that we value collaborative research and interdisciplinary research. And I encourage students to think more openly and broadly about their chemistry interests. and not confine yourselves into one kind of a box. So our students receive lots of awards, external awards from various foundations and agencies. We also have internal awards, UB awards, fellowships that come with extra additional money for your stipends, or as an honor that you can put on your CV, that helps you with the job search later on. Students graduating from program go to find good jobs. This is just a list of places that our students have gone to in the last few years. All kind of chemical companies, universities, and so forth. I'll tell a little bit about our PhD program. It's a 5-year program, typically, on average. First year is about taking classes and getting that foundation, and then after that, it's all focused on research. Okay? All of our students are financially supported. So every student in our PhD program is supported through some grant, either research assistantship, teaching assistantship, fellowship, or so on. And the salaries are about $27,000, or could be higher if there is additional fellowship support. If you're interested in applying, this is the website. Basically, you can go to our website, departmental website, and the link will be there. Master's degree is not required for PhD. We do not require GRE scores, and your application fee will be covered, right? So you won't have to pay for the application fee. So we try to, as much as we can, to reduce financial burden from the applicants, because we know it could be a lot of money when you apply to multiple schools. Priority deadline for this year, January 15th. It's not the actual deadline, but it's a deadline if you want to be considered for additional fellowships that can potentially increase your support stipend. And if you have any more questions, Professor Tim Cook, who is actually hosting right now, who is advisor of one of the graduates of University of Delhi. Professor Tim Cook is our Director of Graduate Studies, so he'd be happy to answer questions about the graduate program. Or you can contact me. And also, I have UB chemistry pens here, so after the lecture, please stop by and pick a pen. All right, now let's talk about science. So my talk is about nanostructured materials from bottle brush copolymers. So first I want to introduce what a bottle brush copolymer is. So bottle brush copolymers are unique molecules. They have a nonlinear architecture, and they're illustrated here. So typically these polymers have a long polymeric backbone and then shorter polymeric side chains grafted onto the backbone from almost every repeat unit. Right? The grafting density has to be high so that the steric repulsion between those side chains forces the backbone to stretch out, and the molecule adopts the cylindrical shape in solution. So it affords you a shape factor and rigidity that you don't necessarily see with linear flexible chains, polymers. Right? So these molecules are very big. The typical molecules we work with have molecular weights in the millions of grams per mole. So they're big enough that you can visualize them individually. So this is atomic force microscopy image of bottle brush copolymers deposited on a surface, microsurface. And every particle here represents a single molecule, a single bottle brush molecule. So we like bottle brushes because they provide us with a shape control. Their molecular dimensions are on nanometer length scale. So they're ideally suited for the preparation of nanostructured materials. And they exhibit some other unique properties like low density of entanglements. It just means they don't get tangled up in the melt, which allows them to move around and organize during the self-assembly process. So what do we do with bottle brush copolymers? So there's another topic I want to introduce first, and this is the interfacial curvature. So whenever you bring molecules together to make a material or a structure, one of the important factors that controls the morphology of the structure is the interfacial curvature. Right? So if you look at the self-assembly of a block of polymers, so this is an example of a block of polymer, two different polymers linked together through a covalent bond. So these types of polymers, because most of the polymers don't like each other, they try to get away from each other, but they're covalently connected, so they can't really get away from each other, right? So if you mix oil and water and shake it, oil goes one side, water goes to the other side, they're phase separating, right? So polymers like to phase separate too, but they can't because they're covalently connected here. So as a result of that, they end up forming structures on the length scale of their molecular size, which for linear polymers, that would be tens of nanometers. So the important thing here is how do we generate various morphologies from this linear chains that don't have any shape? And one way to do it is to control the length ratio between the blocks. In fact, that's the only way to control it in linear polymers. So if you start from a symmetric structure, you typically would form, if you're in solution, you'll form a bilayer. If you're in melt, you'll form lamella phase. If you start increasing the asymmetry, let's say we make blue bigger and bigger and bigger, the interfacial curvature shown here will start bending towards the other block. And so as a result, you start making structures with curved interfaces. So this is a flat interface. This is a curved interface. There's more curvature here than there is here on average, right? And so as you make them more and more asymmetric, you start making structures with higher and higher curvature. And controlling interfacial curvature is very important because that's dictating the morphology of the material, and morphology of the material is dictating the properties of the material, right? So we do a lot of fundamental studies trying to understand how to better control this self-assembly process. And with the linear systems, there's only one handle. But as I'll show you with bottle brushes, it's a very unique system, a shape-controlled building block that allow us to do things that you can't do with linear systems. So now that I've introduced interfacial curvature in a bottle brush copolymer, I want to compare two systems. One is this cylindrical micelle that you can form by the self-assembly of a linear diblock copolymer. So if you have a linear diblock copolymer, and you, let's say it's one side is hydrophobic and one side is hydrophilic, and you put it in water, depending if you choose the right ratio, it will organize into this kind of a cylindrical structure, right? This is called a non-covalent assembly. So the chains come together, but there are no covalent bonds between them. Okay, they're just aggregated in a certain form or shape that's dictated by the length ratio between the blocks. Now, because this is self-assembly process, all you need to synthesize is this guy right here. And then once you put it in water or in some other selective solvent, it spontaneously organizes into something like this, hence it's called self-assembly, right? Yes, this is, the water, the self-assembly in water is a bit more complicated. So this is a hydrophobic, hydrophilic groups, so there's no, there are van der Waals interactions, there's no hydrogen bonding, but there's a hydrogen bonding in water. So typically when hydrophobic domains separate from water, it's an entropic process actually, not enthalpic, because of the structure of water molecules around hydrophobic groups. But you don't need to have strong interactions here. Any weak interaction will do because there are many, each polymer has many repeat units. And so even small interaction between repeat units adds up to a very large delta H. That's a good question. Though these chains they're fairly small. They're typically below entanglement length. Yeah. Because this is rigid, the entanglement molecular weight is not known, but what is known is that because of their rigidity, they don't entangle much. And so they are able to order very well. But we'll talk about that later on, okay? So what I want to compare is the cylindrical micelle here that's formed from the self-assembly of a simple linear diblock copolymer. It provides easy synthesis. There's no length limitation. In fact, you can't control the length. Like you can't tell it to stop. It's just going to go as far as it can go. You need two components, let's say hydrophobic, hydrophilic. And And because it's a self-assembly process, it's a bit sensitive to functional group modification. So what that means is, if I introduce some, let's say, charge group in here, I will completely perturb the balance. And I might not make cylindrical micelle anymore, I might make something else, right? So it's a very delicate balance of interactions. With the bottle brush system, it also provides you the same shape factor. It's a cylindrical structure, right? But everything is covalently connected together. So I would call this covalent assembly. It's covalently connected because that's how we synthesize it. Right? We make this is one molecule. So it has a controlled length because we control it during synthesis. It's very robust, meaning that you can put different functional groups and it's not going to change the shape of the molecule because everything is covalently connected together. The limitations are, of course, we can't make it too long because the synthesis becomes very difficult and characterization becomes very difficult. But most of the time, we don't need the structures to be very long. And this is more difficult to synthesize than this, or it was. But with the recent advancements in polymer chemistry, this synthesis becoming much and much easier and more. And in fact, it's becoming so routine that there's so many people now working in this area. This area is kind of exploding now in polymer science. So what we've done with these molecules is few things. And I'll tell you like few stories to give you examples of things we use these bottle brushes for as building blocks. Now, so number one, we wanted to take advantage of their cylindrical shape, okay, and use them as templates to create tubular structures with well-defined dimensions that are otherwise very difficult to prepare. So the idea here is that we take a bottle brush and we synthesize a bottle brush with a side chain where each side chain, this is a side chain, has 3 different blocks. It doesn't have to be 3, it could be 2, but I'm showing you this example where it has 3. The block that's closest to the backbone, the red one, is polylactic acid. It's a polyester, so it's hydrolytically degradable. That's important. The block that's on the outside has these coumarin groups, which we're going to use for photo cross-linking. And the middle block, the blue one, is some functional block that you want to end up on the inside of your tube. In our case, it's a protected carboxylic acid. So now if you take this polymer, you subject it to UV light, all of these coumarin groups are going to react with each other. They dimerize with a 2+2 cycloaddition, and you're going to cross-link the outside and kind of create rigid cross-linked shell. Right? And then you hydrolytically remove this red part, and you end up with a cavity. So you end up with a tubular structure where the length is controlled by the length of the bottle brush, and the diameter of the pore is controlled by the length of this red block, right? So each tube is a result of, is templated by a single bottle brush molecule. So you get very good control of the dimensions and functional groups. The blue block, because the way it's placed, is on the inside of the structures. So we've done various iterations of this. We've put hydrophilic groups on the outside and made the interior hydrophobic. We made exterior hydrophobic and put charge groups on the inside. So you can do all kinds of variations. All depends where you place those functional groups with respect to each other. So a very good tool of making these objects that are otherwise difficult to make. And we've tested them, their interactions with living cells. We also use them for selective transport of molecules based on size. So we've transported small molecules that can fit in the cavity and exclude big molecules that can't. So you can do all kinds of things with this methodology. So this is number one. This is just using single bottle. There's no self-assembly here. This is a single bottle brush, and we're using it as a template to make a tubular object. We've also been interested in self-assembly. So how to bring these bottle brushes together to make a periodic structure. So this is examples of melt self-assembly. It means there is no solvent. You just put a polymer, you heat it above glass transition temperature to give polymers mobility, and they will organize based on the interactions between the polymers and their sizes and so on. And so it turns out that this bottle brush copolymers, even though these are huge molecules, these are 2 million or more grams per mole molecules, they're able to organize very well because they don't entangle due to their rigidity. The analogy I like to give to my students is like the bottle brushes are like, maybe it's not a good analogy here. It's like you know what a spaghetti is, right? Everyone knows spaghetti is. So if you look at spaghetti before cooking, you can pick out one spaghetti from the box and nothing else is stuck to it, right? If you cook spaghetti or noodles, and then you try to pick one noodle, it's very hard. Everything is entangled, right? That's the entanglement. So the flexible chains entangle, rigid chains don't entangle very much. And so this bottle brush, which is not good for mechanical properties actually, but it's good for self-assembly. So they're able to organize into these beautiful periodic structures. How do we know these are beautiful periodic structures? We analyze them by what's called ultra-small angle X-ray scattering. And it's just like X-ray diffraction, but for larger length scales. And we see these periodic peaks indicating this is a layered, highly organized, layered structure. The nice thing about this is that because bottle brushes are so big, when they organize, this dimension is also very big. It's on the order of 100 nanometers, 150 nanometers, and more. And what that means is that this material, because of the periodicity, now starts interacting with visible light. Right? So these structures, after self-assembly, adopt this color. Well, the color depends on the length, the periodicity here. This one is blue. I think the domain spacing is about 150 nanometers here. And the color is solely due to the structure of the material. There is no pigments or dyes here to absorb in the visible light. This is similar to structured colors in biology, like butterfly wings and so forth. The color comes from the structure of the material. You can also manipulate the structure a bit. Instead of having a symmetric bottle brush, you can have asymmetric bottle brush, so longer side chains on one side, shorter side chains on another side, and that forces the curvature, and you are able to generate different morphologies. So one thing we wanted to explore is, normally I showed you an example here of how to attain different morphologies, but normally it's very difficult. So these bottle brushes tend to, because of their rigidity, they tend to pack into flat interfaces. So they make layers, lamella phases. But it's very limiting, right? There are other interests in other morphologies. So we wanted to explore other avenues to controlling the interfacial curvature. And one thing we thought to do is to change the interface between the blocks. So instead of having a sharp transition from red to blue, we designed a bottle brush copolymer that has a gradient transition from red to blue, right? Okay, how do we make this polymer? So we start with two what's called macromonomers. It's a polymer, it's a short chain with a polymerizable group, another short chain with a different polymerizable group. This one is an exonorbornine, this is endonorbornine. This polymerizes faster than this. And so when you add them together in the presence of the catalyst, this starts polymerizing first, shown here. Well, this one is not polymerizing. At some point, you start getting incorporating this chains as well. This is all consumed, and then this continues polymerization. So we follow this by NMR, and we can monitor conversion of this and this individually, and that's how we plot the conversion with relative to time. And this tells us we're creating a gradient structure. It turns out that these gradient polymers exhibit very different self-assembly characteristics than their counterparts with sharp interface. So this is a phase morphology map, I should say, of a bottle brush copolymer that has a sharp interface. Okay, red or blue goes to red. What is a morphology map? So this is a composition. This is a volume fraction of polystyrene. Basically, it tells you how asymmetric the polymer is. This is not important, this length scale. This dots here, or diamonds, represent lamella phase. Squares are cylindrical phase. and the circles are disordered phase. So you can see that in most of this region, you form a lamella phase. Right? That's what we've seen before. These are rigid structures that like to pack into layered interfaces. How do we know what phases are? Well, we use X-ray scattering to characterize these materials. Typical, it varies. So persistent length depends on the side chain length and so on, but it can be as big as 30 to 40 nanometers. Yeah. No, these are not that big. These are actually less than 100 nanometers in length. Yeah. If you come, okay, so so what I was going to say here is that this wide window of lamella phase is consistent with theoretical predictions. So if you look at the phase diagram, there's a computational theoretical work saying that if you have a block copolymer with increasing rigidity, as you increase the rigidity, this lamella phase widens. Okay, and this is what we observe. So this is solely due to the fact that these are rigid molecules. If you look at the gradient bottle brush copolymer, this morphology map is very different. See, now the lamella window is very small, but we generate a lot of cylindrical phases. This is the cylindrical phase. And we also see what's called a gyroid phase. This is a very rarely observed network morphology, which was very interesting to see, and it's unambiguously identified from X-ray scattering. So it's a much richer morphology phase, and we get a very large window for cylindrical morphology. Now, cylindrical morphology is nice because you can remove the cylinders post-self-assembly to generate porous structures. Right, so it's ACM images of a cross-section parallel to the channels and perpendicular to the channels, showing nicely hexagonally packed morphology. So these are ways to manipulate interfacial curvature and morphology by playing with the architecture. So we're not changing repeat units. We're not even changing the fact it's a bottle brush structure or the length of the side chains. We're just changing the gradiency of the composition. So we learned a few things from the melt self-assembly. We applied them to make some photonic materials, some porous membranes, and we wanted to take these lessons to the solution self-assembly and see if the same curvature control can be achieved in the solution self-assembly process. I gotta keep track of time. All right, so in the solution self-assembly, things are a little bit different. So here you have, again, it's a polymer with two different components. It's a hydrophobic polylactic acid chains and hydrophilic PEO-like chains. And we wanted to see whether we can achieve curvature control by playing with the diameter of the bottle brush components. So it turns out, the long story short, is that these molecules organize actually very well in solution as well. And based on the composition, you can form cylindrical micelles, big, large spherical micelles, or small, compact spherical micelles by playing with the size of the hydrophilic group. Right? This is kind of similar to surfactant self-assembly, where one can calculate packing factors and so on and predict the morphology. We've developed a model for these molecules to be able to predict the morphology as well, based on studies on small surfactants. These shapes, well, these are all dilute. This is dilute solution. If you do it at higher concentration, you will start forming different morphologies. Yeah. You can get lamella. So we've done lamella as well. So if it's more symmetric, so here, lamella morphology in solution would form a vesicle, basically, the bilayer vesicle. So we've seen that, but they're very big because these are rigid molecules. It's hard to image them by transmission electron microscopy. So I want to talk a little bit more here. So I want to show you like what we're seeing here. These are cryo-TEM images of these micelles formed from bottle brush copolymers, and you can appreciate the rigidity of these bottle brushes. So this is a hydrophobic core, okay, that's shielded with this. These are hydrophilic parts of the bottle brushes sticking out of the core. And if you measure the length of these hydrophilic brushes, they're indicating that this side chain is almost fully stretched out, because we know how many repeat units is here, and we know at full stretch how long that should be, and they correspond to each other pretty well. So one of the interesting things about this micelles is that, first of all, we can create a very uniform micelles, and two is that they're actually more stable than micelles prepared from linear block copolymers. So the stability of micelles is measured by what's called critical micelle concentration. And these are more thermodynamically stable, but it allows you also to do other things that you can't do with linear systems. This is molecular weight of the individual polymers. So we measure them by GPC light scattering. Yeah. No. This is molecular weight of individual polymer, no aggregation. So each polymer is this big. So what we've done is we know, and we use gel permeation chromatography coupled to light scattering detector. We measure the size of each chain, and then we can also measure the size of the aggregate, and then we divide the two, and you can calculate the number of chains in the aggregate. Yes, way below mine. It's in nanomolar. Yeah. Okay. Why? So this is why micelle stability is important. A lot of polymeric micelles are used for drug delivery applications, right? So you encapsulate hydrophobic drug in the micelle. But the problem with all these micelles is that once you inject them into your bloodstream, it gets diluted. And once it gets diluted, it falls apart, right? Because you go below CMC. So low CMC is important, right? Stability is important. But I'll show you in a minute how you can make them even more stable. So I want to show you this cool example that you don't see with linear systems. So we compared here two bottle brushes. They're the same. The only difference between these two bottle brushes is the length of the hydrophilic backbone. So it's long here and short here. It's 50 units here, 150 units here. And we looked at their self-assembly. So the difference between them is huge. So this is about 60% hydrophilic. This is 85% hydrophilic, right? So if this was a linear system, you'll see completely different morphologies, because they're so different in terms of composition. But with the bottle brushes, because the curvature is dictated by the diameter of this here and diameter here, which is the same for both of them, the size of the core, micelle core, in both systems is the same. So the curvature is the same. The only thing that's changing are these brushes protruding from the core, and they correspond to the length of this hydrophilic backbone, right? So one thing we've done is we kind of made this a little bit more complicated and added additional components to it to study packing of these brushes inside the micelle. And this is just one slide I want to show for synthesis, because we spend a lot of time making these molecules and I never show any synthesis. So this is one synthesis slide just to give you an idea how we make these polymers. So for example, in this case, we wanted to make this structure. So this is a bottle brush where you have one side, you have double PLA chains coming from every repeat unit, and at the end of each PLA chain is this coumarin group. On the other side, we have this hydrophilic PEO-like chains that are branched as well. So to make something like this, we start here, we make the macromonomer PLA functionalized end groups, polymerize, and then polymerize another monomer with the initiator, and then from this initiator grow here. So a few steps, but we've become, very proficient at this, and while this looks complicated, it's pretty routine in our lab nowadays. So what we've done with these molecules is we thought that, okay, if these are rigid and they're packing into a sphere, right, there must be some packing frustrations inside the sphere that we can take advantage of for loading these micelles with hydrophobic cargo. So we synthesized a series of these polymers with different architectures and different compositions. And what we wanted to study were two things here. One is the reason we incorporated these coumarin groups is because coumarin groups, as I mentioned before, they undergo 2+2 dimerization, and they connect to each other. So we use them as cross-linking units. So if you do aggregation or self-assembly to make a micelle, you can then shine light on it, and all these coumarins will connect to each other, which means now you have a covalently cross-linked object. And now it will not fall apart when you inject it in your bloodstream, but it's still biodegradable because all of the side chains here are based on the polylactic acid. It makes it more stable. But we also use this cross-linking to probe how close these chains are to each other inside the core. So that's the main reason we did it, to try to understand the packing frustrations inside that micelle. So what we've learned from these studies is that, try to illustrate it here, as you make this hydrophilic group bigger and bigger and bigger, so you make the molecule more hydrophilic, it's very counterintuitive. You make it more hydrophilic, so that's this axis. The amount of drug you can load into micelle actually increases. And it increases because when you make this big, you create packing frustrations, and more space inside the core where the hydrophobic drug can go. So at the maximum, you can keep increasing. We can load up to 30%. So 1/3 of the core is composed of some hydrophobic cargo. And if you keep increasing further, it just drops because at that point, it doesn't form a micelle anymore, efficient micelle. The hydrophilic head is so big that it can't form a micelle. So we explain it here. This is a difference between a flexible amphiphile and a rigid amphiphile. In the flexible system, if you start from here and you make hydrophilic chain bigger, the molecule will adjust because it's flexible. Yes. So if you make this bigger, this will contract and you would just form a different diameter. If it's a rigid amphiphile and you make hydrophilic group bigger and bigger and bigger, you create packing frustrations inside the micelle. And this is packing frustrations that can be exploited by the hydrophobic cargo. So you can increase the loading capacity. So again, another example of how polymer architecture allows you to control the curvature and the morphology and the properties that you can't access from flexible linear amphiphiles. Okay, now I'm almost running out of time, so I want to go through this quickly. This is the other area that we are very interested in. It's a new area in the group, and these are nanostructured polymer networks. We're interested in polymeric networks because they're very important for a lot of applications that rely on transport. So if you're making any kind of membrane, and you want to transport a molecule, ion, electron from one side to another, you need to have a continuous pathway, right? Now, you can generate that continuous pathway by making a straight channel. That's the best way to do it. But this is practically or technologically very difficult. It's very difficult because you have to control orientation. If your channel is oriented this way or this way instead of this way, then there will be no transport. The advantage of network systems, or three-dimensional systems, is that you don't have to worry about orientation. And for a lot of these applications, there are examples where network morphology is used, or it's bulk heterojunction solar cells, water filtration membranes, ion conducting membranes, like Nafion itself has a network-like structure. In all the structures, you have a network, but it's you don't need an ordered lattice. Otherwise, it doesn't need to look like this beautifully ordered structure, right? As long as it's interconnected and your domain sizes are controlled, the lattice order doesn't matter. So how do we access polymeric networks? Well, there are two ways to look at it. Like, you can approach it from two different angles. One, you can say, well, you can use block copolymer self-assembly or surfactant assembly. That's true. I just showed you can make network morphologies. The problem, of course, is that the network morphologies exist in a very narrow compositional window. That's very difficult to target. You can do kinetically trapped phase separation. That's a very robust way of doing it, actually. One way to do it. But it's hard to go down below 10 nanometers here in terms of size of these individual domains. On the other end of the spectrum, we have this molecular construction of networks. So molecular organic, metal organic frameworks, covalent organic frameworks, polymers with intrinsic microporosity. They're all very different, but in the end, they're kind of the same concept. You have rigid molecular building blocks that can't pack very well. And so when you put them together, you end up with cavities between molecules. You end up with highly porous systems where pore dimensions depend on the size of your building block. And because your building block is a small molecule, you end up with pores that are 2 nanometers or smaller, which is very interesting for a variety of applications, gas storage, gas separation, so on. But it's also limiting in terms of what it can do. So we wanted to explore this gap and maybe take some lessons from here and maybe add processability of polymers, kind of combine them two, and attack this space that's been unexplored. So this is one idea that we explored. This is an initial idea. I just show you because it's in contrast to the second idea I'm going to show. Basically, we said, okay, this is very simple. What if we mimic something like this, but instead of small, rigid molecular building blocks, we're going to use big, rigid molecular building blocks. This is where we said, let's use a bottle brush as an network interconnector, attach some reactive groups on both ends, so then when these groups can react, they make a network. We remove solvent, end up with porous structure if it's rigid enough. And it does work in a way. The synthesis is quite complex here, but we can make a bottle brush with reactive groups. We also need here another reactive orthogonally cross-linkable group in this block to make it even more rigid. And we do end up with this sponge-like porous structures, okay, after removing the solvent. So this method works in a way we get fairly narrow pore size distributions. This is analysis by gas absorption, nitrogen absorption analysis. The smallest pore size we get about 10 nanometers. Okay, so it's a work we're moving in the right direction, and we control. The important thing is here I want to show you is that the pore size is controlled by the length of the backbone. Okay, so if I go back to this cartoon, you can see that if I make this longer, my pores inside should be on average bigger, right? All right, so this method is working, but it was a bit of a, the synthesis was complex, it was kind of not very scalable. But we wanted to create a system that's more robust and more scalable. And we came up with this approach, which is kind of very different from the first approach, but in a way it works better. So here, instead of using bottle brushes as network interconnectors, we're using them as precursors to cylindrical pores themselves. Right? So we're going to use a bottle brush. We're going to make a bottle brush that's composed of some degradable polymer. This is the bottle brush. We're going to dissolve it in some cross-linkable solvent or matrix. And then we're going to dissolve them, and we're going to cross-link the matrix as quickly as possible without allowing these bottle brushes to aggregate or phase separate, trapping the structure as it was in solution. This is at very high concentration, so this is like 50 weight%. So these are essentially gels before we even cross-link. So if we do that, we're hoping we trap this percolating brush network structure, which we then can if we need to make a porous structure, we can etch these cylinders out using hydrolysis or thermal degradation. So this was the concept. I'm going to skip synthesis here. What I wanted to point out is this is the key step here. So we cross-link the system, and then we need to do the etching. This is the key step. Why? Because we etch using hydrolysis. The matrix is hydrophobic, it's polystyrene. Water cannot go through polystyrene. So in order for us to be able to etch through this sample, get rid of all the channels, they have to be interconnected. If they are not interconnected, the water will not be able to access them. So this is the biggest evidence that everything is interconnected, is that this peak right here, this is the carbonyl peak corresponding to PLA. It's completely gone after hydrolysis. This is a TG corresponding to PLA, also gone after hydrolysis. We measure the weight loss. Weight loss is about 50%, right? Corresponds to the weight of the PLA that was in there. But the dimensions or a shape of these monoliths do not change, right? So they don't shrink, they don't become powder, they stay the same, they just lose 50% of weight, and we'll lose the signature in IR and DSC, right? Which is telling us we're removing all of the PLA, but the structure is not collapsing. It's a good sign. So let's go through this analysis. I didn't mention this, well, I'll mention this here. So you can start with a simple PLA bottle brush. This is very easy to make, 2 steps. And both reactions go to almost 100%. This is polylactic acid bottle brush. We dissolve it in commercially available styrene divinyl benzene matrix, cross-link, etch out, then analyze the porous material with nitrogen adsorption analysis. This is an isotherm. It tells you that this is a mesoporous structure. And this is pore size distribution you can map out by modeling this. So what this is telling us is that if you can just use simple PLA bottle brush in a styrene divinyl benzene matrix, and you can get mesoporous material with 28 nanometer pores. Okay? This is promising. Now this is in itself effect of a bottle brush architecture. If you try to do the same thing with a linear polymer chain, not a bottle brush, just linear PLA, you're going to get no porosity or no surface area. Why? Because when you cross-link, those PLA chains will aggregate and you'll create macro-scale structures. So they'll undergo macro phase separation. You'll etch, you will end up with giant pores and no measurable surface area. So this in itself shows the effect of the bottle brush structure. But what was more fascinating is that once we start incorporating reactive groups along the periphery of this bottle brush, this will start dramatically changing. So what we've done is we've incorporated these reactive groups on the periphery. I'm going to show you progressive increase. So this is 5%. So 5% of these N groups were modified. What this N group does is that it's reactive. So when the matrix is cross-linking, it reacts with these groups and fixates the bottle brush to the matrix so it can't move anymore. And if it can't move, it can't aggregate with other chains, right? So it allows us to fix it. So if you incorporate 5% of these reactive groups, your pore size drops to 18 nanometers. If we put 10%, your pore size drops to 13 nanometers. If you incorporate 50% of these groups, your pore size drops to 6 nanometers. And if it's fully functionalized, your pore size is now 4 nanometers, and it's a very narrow pore size distribution. Like all of the pores are between 3 and 5 nanometers. The 4 nanometers is about the diameter of this bottle brush, right? So in this system here now, we're replicating the molecular dimensions of the bottle brush building block and preventing any aggregation or phase separation during this cross-linking process. It's a competition, and you need to trap it before it has a chance to aggregate. All right, so I want I'll just wrap up quickly. So what I wanted to point out that we've advanced this further to improve the thermal stability. So this structure, styrene divinyl benzene, is not very thermally stable. The porosity is lost if you heat it to 100 degrees. And that's because glass transition temperature of polystyrene is around 100 degrees. So we've tried to improve that by switching polystyrene to something with higher glass transition temperature, and that improves it a little bit, but still at 120, porosity starts dropping. So we've used a different system. Instead of styrene, we use this benzocyclobutene styrene, and this is a very interesting system. At room temperature, up to 200 degrees, nothing happens to this group. So you can polymerize this double bond just like before, but at above 200 degrees, this cyclobutane ring opens to create a diradical, which then cross-links. Right? So this is a further cross-linking step. So using this monomer, it's the same procedure. We add one more step. It's called thermal baking. We cross-link the matrix further to make it even more rigid. We do that because we want to improve thermal stability of these materials. And in this case, it actually works really well. There's no pore collapse up to 300 degrees Celsius. So we can take this nanoporous material. I'll show you, we did some scattering, but here. We take this nanoporous material, 4 nanometer pores, we heat it to 300 degrees Celsius for 24 hours, and nothing happens, very stable. SCM tells us these are very nicely, distributed. It's random networks, but there are no big aggregates or pores. Like they're pretty uniform. We also I'm skipping here. We also replaced this non-degradable backbone with something degradable. Okay, so this is all carbon backbone. We replaced it with carbonate backbone. And that in itself, this is synthesis. I'm going to skip through this. That in itself also helps, okay? Because when you have a non-degradable backbone and small pores, the backbone is still in somewhere in the material. And if it can't diffuse out, it will plug the pores and decrease your surface area. With the degradable backbone, we're able to achieve over 600 square meters per gram surface areas, which for polymer samples is quite impressive. Very small pore sizes, again, in that less than 10 nanometer range that's difficult to achieve with any other method, and with pore volumes that are approaching the theoretical limit in our system. And again, we maintain narrow size distributions. So this is an exciting new methodology that we're starting to explore to create other nanoscale networks, not only for making porous membranes, but also making membranes for ionic conductivity and so forth. And our analytical chemistry colleagues, for example, are excited to try these materials for chromatographic separations, where you need high temperatures, gas chromatography and so on. So I would like to thank students who've done all the work. KJ here, who's graduated now, she did all the work in make nanoscale networks. And I would like to thank funding agencies and you for your attention. I'd be happy to take any questions. Sorry I went a little over time. Thank you. Yeah, we haven't looked at semiconducting polymers, but there are some studies where people have put semiconducting side chains on bottle brushes and used bottle brush structure to organize semiconductors. We haven't worked much in that area. It's an interesting area. Yeah, you can even put you can make a bottle brush where one side has a P-type side chains and the other side has an N-type side chains. Combine them in one molecule. There's a lot of, this area is kind of exploding now because this platform provides for many opportunities to like tune the material structure. Hmm? Yes, yeah. So when we started, there's very little work in using these bottle brushes to make materials, but in the last 20 years, it's been exploding. Yeah. In the self-assembly. Yeah, we don't have any charged groups in there. If we did have charged groups, we haven't looked at the contrarian effect. Yeah. Our hydrophilic block is non-ionic, and we chose it on purpose because it's simpler. With ionic structures, there are other things that come into play. Yes, yeah. The picture gets more complicated, and so we tried to explore the effect of architecture, so we wanted to eliminate other variables, but once we understand the effect of architecture, we can take it further now and incorporate ionic groups. There is some work in bottle brushes with ionic side chains. They exhibit some interesting properties. Yes, you have to, well, if you do melt self-assembly, it doesn't matter much what solvent you start with because solvent evaporates before self-assembly, but if you do self-assembly in a solvent, then the nature of the solvent is very important, yes. Yeah. We do it mostly in water, but you can use other solvents. It just depends, it has to be a selective solvent, so which means the solvent has to like one polymer, not the other, basically. To force the aggregation process. Yes. Let's see. This is SEM, this is scanning electron microscopy. Yeah, so it's a porous sample. What we do is we want to look at so SEM looks at the surfaces, but we want to look at the inside. So what we do is take our sample, which is a monolith, we break it, and then look at the surface of the sample we just cracked. And so this is what the surface looks like. And in some cases, most of them are bundles of bottle brushes. They're not individual, but you can see in some areas, these are the network, the junction point between the brushes. That's a very good question. I think this is, I should have written it, now I don't remember. It's in the paper. It's about 4 times bigger, I think. I should write that. We've done some studies. We haven't done biological studies, but we've looked at drug loading and drug release, rate of drug release, depending on how the cross-linked they are. But we haven't done. We've done some in vitro studies with other systems, but we haven't explored much. So we chose PE or PLA for a reason, right? So PLA. So this PLA and PEO, you just have a linear block component. It's a commonly used material. So we just wanted to have a bottle brush analog of that. Don't forget about the pen.
Yeah, there are some pens or utility of that. And since I think the number of activities is not equal to the number of pens, I think I will pass that those coming forward.
I have more.
Those don't get pen, you can catch me in my mouth. Then I want to prioritize this.
And if you're interested in applying to graduate school, please visit our website. If you have any questions, either let me know or Professor Tim Cook.
Thank you.